Hi everyone, welcome to the Learning on Graphs and Geometry reading group, and today we're discussing the paper Reflected Diffusion Models by Aaron with himself. Let's go.
Stefan Arman. As a quick recap, I'll cover a bit about standard diffusion models. Hannes has told me that a lot of you have already seen a lot of this stuff, but I think it's still important to establish a common framework and common terminology. So for the regular diffusion models, you start off by noising your data through a stochastic differential equation. This appears as something like this dx given a drift term f and a scalar diffusion coefficient g. And by applying this known f and g, you can take your data points, which let's say our images on the left, to a random noise, such as the images that you get eventually. And yeah, the key point is that these f and g are fixed coefficients. It can be something like this OU process given below, where the f is negative x and the g is a single 1. And this allows you to control the effects of the stochastic differential equation. And as we'll see, another important aspect is that you can control the transition probabilities, which will be useful for score matching. And the key idea behind diffusion models is that you have this SDE, which takes data to noise. And of course, there's a way to reverse this SDE and take noise to data. The key idea behind this is that you can take the f and g and you basically construct this new reverse SDE. And the only new thing is this gradient x log probability, which is called the score function. And yeah, this is not a deterministic reversal of your individual data points, but it is a reversal of the distribution. So if you take your noise distribution, you apply this SDE, you'll end up with your data distribution, although you might not end up with the same data points. As mentioned previously, the only new thing about this SDE that we have not seen yet, we know what f is, we know what g is this gradient of the log probability function. This is commonly known as the score function in the literature, and we can actually learn this using neural networks. The key idea here is that if you want to learn PT, this PT tends to be a bit more restricted to learn because you have to maintain the fact that it integrates out to 1, it's greater than or equal to 0. These end up being a little bit hard to enforce in a neural network. Whereas a score function, you basically can model it with a general neural network. How do you learn the score function? Well, a very natural loss is this kind of the supervised learning loss that people use, which is called score matching. And so the S here, I'm not sure if you can see my cursor, but if this S theta is your neural network that represents your learned neural network score function, then the idea here is you want to minimize this expected value with respect to the probability distribution between your S theta, which is your score neural network, and your ground truth neural network, ground truth score function here. Chat function. Oh, we can see the cursor. Okay. Yeah, so this all makes sense. It's a very natural thing to do. Of course, well, this gradient of the log probability is intractable as the ground truth, which is frustrating, but we can use the fact that our distribution is structured. In particular, we have that, well, yes, this PT is equal to this convolution of your P0, which you can think of as your data distribution, with this SDE transition kernel. So if you can imagine you take a data point, you randomly apply your SDE noise, which is given by this transition kernel, and this gives you your PT distribution for each time step t. So we can use the fact that our distribution is structured in this way, and we can rewrite the above loss into this slightly more complex version, which is called the denoising score matching loss. The key idea here is that we can sample x naught given our optimal data distribution. We apply our transition kernel to it here, and then instead of matching S theta with your ground truth gradient of the log probability score function, well, you match it with this transition kernel instead, which is given here. And the key idea here is that this transition kernel is, we can basically get it in closed form as a transition density, whereas the gradient log probability is generally intractable. And thus, since these two losses are equivalent, it means that we can effectively learn our gradient, our score function using like this new, nicer type of loss. Such putting it all together, we learn our noise, we learn our S theta, and then we can follow the generative SDE given here, where instead of the ground truth score function, we have our neural network score function. Okay, we start from random noise, and then, okay, I guess, then we can start from our random noise, use our ground truth score function, or not ground truth, our neural network learned score function, and this allows us to generate samples by starting from noise and following this SDE. I guess another important point I want to stress in our talk is the fact that diffusion models are also very useful, primarily because of this aspect of them called diffusion guidance. For diffusion guidance, the key idea is if you instead want to model a conditional distribution, let's say P of X given C, where C is some sort of conditional variable. It could be, you can think of it as a latent class, so we'll say panda, or you can think of it as a text input like avocado chair. Well, because we know that this conditional distribution breaks down proportionally to this product of distributions by Bayes' rule. So in particular, this distribution is equal to this px times this pc given x. This is all by Bayes' rule. Well, if we take the gradient of log probability of both sides, we have that this the score function for our conditional distribution is equal to our general score function given here. And then we also have this other score function with respect to the class given the input sample. So this is like a classifier, basically, this thing right here. This PC given X is a classifier. We can take a score of the classifier. Score network and the ground truth score network and a learned classifier. And then by applying this, we can effectively force our samples to be closer to our given class. So this allows us a good deal of controllability over our score network of our generative model. So this allows us to generate pictures of dogs or huskies given here, which is useful in practice. So now everything I've said so far makes sense in a theoretical framework. Everything works out, but sometimes the real world gets a bit ugly, I guess, is the main issue. So if we re-examine our generative SDE, well, in practice for our generative SDE, we need to break it down a bit in order to simulate it on our computers. In particular, we have to discretize it given its Euler-Maruyama scheme given here. I think all of it generally makes sense. You basically just take finite steps of your delta t and your BT. Your BT here is instead like a random sample from a normal distribution. And you have to take these individual steps. And the issue here is we have three main issues. First of all, this S theta is not learned perfectly. As generally speaking, we can't guarantee that our S theta matches our distribution, our true score function generally. This is something that's hard to do. Another issue is that our time step is discretized, which introduces some more numerical error. And finally, we have just random chance given our BT. So if we just sample our BT or Brownian transitions or our Brownian increments, well, our Brownian increments you can just get unlucky. You just get a couple very bad pulls, and then this will cause numerical error. In effect, what you get is that when you sample like this, this can cause our sample to go to low probability regions. So if we take our distribution evolution given previously, we follow let's say our discretized SDE, well, we take a step, we take another step, and then eventually we can start get this drift where we eventually go out of distribution a little bit, and then we're completely out of distribution here. And what happens once we're out of distribution? Well, back to our original score matching loss, this is how it looks like in general for you weight it by time step, you do it everywhere here. Well, the issue here is that our score matching loss in practice, or the way to think about it is, we're weighting it by the PT value here. And once the PT value is low, it becomes very difficult to learn our score network as theta. And in particular, the behavior here tends to be a bit undefined, I guess is the main point. And then once that happens, well, we take previous generative models, like let's say this is the OpenAI guided diffusion model or OpenAI guided diffusion GitHub. And this is some previously reported images from Imagen, and you just follow our generative SDE. This is what you end up getting. Basically, stuff diverges and things like these are obviously not like correct looking images. Yeah, and again, I want to stress that this exists in pre-existing work. It can be reproduced pretty easily. So how do people this? It's kind of a shock because when people post their diffusion models on Twitter, they have these nice looking photographs and it looks very nice and stable. How do people do this in practice? Well, you do this thing called thresholding effectively. And the key idea behind thresholding actually stems all the way back to the original diffusion model papers, which talk about it in terms of a VAE. So in particular, if you consider your Euler-Maruyama discretized step as a VAE, well, you can decompose it as with a mean and a standard deviation. So you take this step, and this is your VAE, so your so-called VAE predicted mean, and then you have your VAE predicted noise, which is this GT times the Brownian increment. Remember, the Brownian increment is your standard normal distribution. So this kind of looks like a VAE is the point. Well, if we want to model images, let's say, and images lie in this image space where -1 to 1, let's say, each pixel value needs to be within a certain boundary. Well, it would make sense, if we have this pre-existing notion of what our output should look like, to make sure that our predicted VAE predicted mean is a valid image. So when we simulate this, we can start off here. If we go out of boundary a little bit, well, then we can say, hey, we just project back. This makes sense. Yeah, and then this form, so we don't ever get out of bounds, so to speak, too much. And so basically, you just modify the sampling scheme, and by projecting the VAE predicted mean to this invalid image space, after each step. So yeah, this is called thresholding, and I guess the main idea behind this is that whether or not your image space is -1 to 1, 0 to 1, or more commonly, as what people will know it is 0 to 255. This is what each pixel value is. You just modify the sampling procedure in order to get this to, so-called to make sure things don't diverge too much. And I think this is a well-known hack. You can see it in a lot of pre-existing repositories. So here, this is the first one here is the original diffusion model repo. They explicitly do this clipping, this thresholding trick, and then you have some more of the recent repos given below. And this was a major point that the Imagen paper from NeurIPS last year explicitly talked about. And then, you just do this, and, it's clearly not the right thing to do. If we want to reverse the diffusion process, this will clearly give something that's not the correct reverse of the diffusion process. But in practice, this ends up helping your results pretty significantly. So if you take this OpenAI guided diffusion GitHub repo from previously, you apply this, well, then your images stabilize. You don't get blank looking images. Same thing with Imagen. If you just apply this, you get a much better looking image, generally speaking. So the key insight of our paper, so to speak, is that when you threshold and you do the stuff, at the limit, it becomes a reflected SDE. In particular, if we take this general threshold Euler-Maruyama step, which is given here, so this is this xt plus fxt. This is all stuff we've seen before, but now we have this projection operator at on the mean after each step. Well, once we take time to go to 0, what this effectively recovers is this reflected SDE. And so we've kind of seen most of the stuff here. We know what F is, we know what G is, we know what BT is, this Brownian motion stuff. Well, the only new thing here is this DLT here. And what is this DLT? Well, the idea here is that this DLT like kind of cancels out all outward pointing velocity once you hit the boundary of your space. So given below here, like what's given below here is what's called like reflected Brownian motion. And the key idea here is that, as you'll see, the Brownian motion will hit this like line, which is like x equals 0, but it will never go past this line x equals 0, because once it hits it, all like force is basically wiped out, and then it continues along its way, and so it will never leave the boundary, so to speak. The idea here. And yeah, once we have this like is this similar to inelastic collision in physics? Yeah, I think a lot of this stuff is very physical and like nature. And I think, yeah, I'm not exactly sure what inelastic collision is in physics, but from what it sounds like, this should be like the same idea here. Yeah, basically. Yeah, so we have like, okay, we have this reflected SDE. And the key like idea here is that reflected SDEs, you have this forward reflected SDE. Well, similarly, you can like reverse it with like another reverse reflected SDE, which I guess is pretty cool. Yeah, so basically you can reverse it. So again, we see that what the main thing that like matters, so to speak, the main thing that like comes up and like will affect our like what's relevant to us deep learning practitioners is that the score function again shows up. And the idea here is that if we can do the same, I think same kind of like diffusion model idea of learning the score function, using it to reverse the whole distribution, then we should be able to kind of port everything over from like standard diffusion models to reflected diffusion models. And yeah, so now the only question that's left, kind of, basically, is how do we do our score matching? And more or less like the same like probabilistic stuff holds up, because the original like probabilistic formulation of denoising score matching was pretty general. We can reapply denoising score matching here, and it's the same formula as we had previously. But the only difference here is that this our ground truth like transition like density is different now. And to see this, we can look at this new kernel here. So if our new kernel is constrained on 0 to 1, and then we apply it, well, eventually go to uniform distribution as follows. Whereas, for a standard Gaussian kernel, it will continue spreading out more and more. And this is just kind of like the difference between our new like density and our old density. So clearly here, really the only thing that we have to do is to approximate this approximate this new like transition kernel like within numerical precision. And once we can do that, we can like do score matching here. So what are some strategies for doing that? Well, well, for starters, one of the ideas here that seems pretty natural is this idea of like summing over all the constituent parts, or sum over paths, so to speak, type of analysis. In particular, if blue is our sort of like reflected transition kernel, well, we can just imagine that we have two sources, like this gray and this lighter gray. And then once we like, sum in, the lighter gray, and in particular ends up being it ends up being the reflected version of like the gray distribution. And where the gray distribution shares the same like starting point as our blue distribution. Well, once we sum up these two distributions, the two gray distributions, it should approximate like what the blue distribution is. And once you take like enough of like these reflected like sources, it'll eventually like become the blue distribution. So more or less, you just sum it up from all the source terms. It's kind of the intuition here. So you have all these source terms, you sum it up. This is given in particular here by this formula. This like the transition kernel is equal to the sum of all the x prime, where x prime is the reflected version of our like xt. And then we take a standard normal distribution as our summation. Each of the distributions is the standard normal. Well, the key insight here is if our value of t is very small, then these normal distributions, you don't have to take that many reflections effectively to get a good approximation of your true transition kernel. So in particular, this strategy works like very well for like small values of t. Basically, at that point, then this becomes like like, you don't have to take that many, you don't have to take that many summation terms. So it's computationally cheap to evaluate. Well, there's another way of doing this in terms of like, how do we score match on a bounded domain? And this comes from the fact that we can kind of decompose like the score, or we can kind of decompose the transition probability using harmonic analysis, basically. More or less, this is like, you have these things called harmonic components over or harmonic eigenfunctions, you might have seen as they're more commonly called. These exist on your bounded domain, let's say 0 to 1, and they satisfy this like Laplacian of fi is equal to some lambda I times fi, basically. So you have like this nice, interaction with like heat kernel, effectively, is what you end up getting. And once you have these functions fi and with their what requisite like eigenvalues lambda I, well, then you can basically construct the heat kernel, or like the kernel, as follows. Which is the transition density. You just basically sum up over all of your fi and lambda I, and you basically like you just take this like product here, where effectively you have this e to the power of negative lambda I times like your quote unquote like standard deviation, and then you just multiply this out by like these two fi's given here. And this is like a
Can you go back a slide?
Yeah.
Okay, no, good.
No.
So like you want to bring the so to say the density, or you sort of want to reflect the density and then use the reflected density when doing your score matching. Is that right?
Yeah.
Plus the density that you usually already have.
Yeah, that's exactly right. The idea is that it's a reflected like Gaussian, and so we just have these various reflected components and we can sum them up together, kind of.
And why is it now necessary to do this Fourier decomposition thing?
Well, the idea behind this is that for large values of t, this reflection, you have to sum up over a lot of reflected terms, basically. And so this can be computationally a bit like taxing, generally speaking.
Okay, yes.
Yeah. So in particular, for this Fourier decomposition, you have the same idea. You have this reflected like Gaussian variable. This is just an alternate form. For what's worth, this is just an alternate form. And basically for large values of t, the sigma t will become very large. So therefore, like for many of the like after a certain like cutoff, basically this value here will cause everything to go to like 0 very quickly. So basically for large values of t, you can take like a bunch of like, or a far fewer amount of like far fewer summation terms here, basically, and you can get an accurate approximation within very quickly. No, there's no Francisco's question. There's no closed form of the reflected diffusion, like, or the reflected Gaussian variable. Then you have to take these like infinite summation terms. It's kind of the issue. Yes. New. Thanks. Okay. Yeah. And it's this is like the more arcane way of like summing it up. So like I think the previous example of doing this like reflection and summing up all these like individual component Gaussians, just a bit more like easy to think of. But for this harmonic decomposition part, at least for like the bounded interval, like it looks something like this. So like in this case, cosine of k pi x would be your harmonic functions, basically. And we can clearly see that once you take the second derivative of this, basically, then the lambda is equal to this k squared pi squared, basically. And this basically gives us our harmonic decomposition, our harmonic representation for our score matching function. Yeah, so we have all this, and we have everything more or less set up, and we've made it effectively scalable. So now how are the results? So on CFAR10, we can generate like pretty reasonable looking images. And as it turns out, we do get a state of the art like inception score in terms of like our generated images. Which is nice. And generally speaking, this is like always like generally speaking, like acceptance score has like been kind of stagnant at 10 or 10 to 10.1. And we show that we can basically get it. And this inches it closer to conditional generation. So for conditional generation, the acceptance score is like closer to 11. But because we like for unconditional generation, we can get it up to basically 10.42, and this is around the same. Yeah, so this is like one of the results that we have.
Why is conditional generation easier in terms of inception score than
generally the idea here? Generally the idea here is conditional generation. You only have to model like 10. You model 10 distribution classes. For each class you model a different distribution, which simplifies the problem basically. And so generally you can say the same results the same things will have better results for conditional generation due to the fact that you're really modeling like you're really like throwing it at 10 different like classes together, which is easier.
Makes sense.
Yep. Another thing that we like noticed is that if you in particular look at like these diffusion guidance methods, well, we looked into a bit more, and yeah, without like thresholding, basically you end up like easily diverging. We believe this is because you have these two score networks, or in general you have like two score networks, and then this ends up causing a bunch more numerical problems. But yeah, with diffusion guidance, if you apply a very low weight to your sampling process, you end up with like pretty divergent samples pretty quickly. So here we have like these four images. I think the second and fourth one like look more reasonable, but the first and third one, these are like clearly diverged. And then another issue is that if you want to apply like a fast sampling method like DDIM or ODE sampling, you also end up with pretty bad results here, and this tends to like degrade performance a little bit at the very least. And yeah, so generally speaking, if you want to do diffusion guidance and these types of constructs without thresholding, you end up with pretty bad images given here. Another point is that for diffusion guidance, one of the ways that we can like make images more clear is by pushing what's called the diffusion guidance weight. So for large diffusion guidance weights, your images should become more like clear. But one of the well-known artifacts of like pushing diffusion guidance weight is that you end up with heavily saturated images like the ones given here. So yeah, generally we can clearly see that for these four images is a pretty clear green bleed through. And the key idea behind here is that even if we threshold, basically if you continuously push mass to the boundary, and once you continuously push mass to the boundary, eventually your images will look more and more like, in this case, green, because like you get closer and closer to the boundary. The boundary is like a heavily saturated image. Conversely, if we do our sampling with our reflected diffusion model, we like train it, we like learn everything separately here. Well, because we properly like account for thresholding in some way, our images end up looking like far less saturated. We don't have this like distinct green bleed through in this case, which allows us to basically generate reasonable looking images at a high guidance weight, whereas previously you would end up with something that's a bit oversaturated. Another interesting point that like should be mentioned is the fact that like typically for diffusion models you have this ODE equivalent, and once you have this ODE equivalent, it allows for stuff like fast generation and stuff like this. For our case, we can basically get the same ODE equivalent more or less, and the key reason for why like this ODE will like go from our domain to our domain, so basically no mass will like bleed out. We can like mimic the effect of thresholding, kind of is like the idea. Well, it's because of this Newman boundary condition that we get when we solve like the PDE more or less. So basically we have this Newman boundary condition, and this implies that this drift term will always like point like we'll never like push mass inside or outside of the boundary basically. So once we follow this ODE, we can take points from our omega to our omega, and this allows us to basically get an ODE equivalent, which bakes in thresholding, I guess is the main idea. And then using this idea, using this this like whole like setup with the ODE, we can derive an equivalent sampling scheme like for our diffusion models as well. So in particular, we can generate reasonably high quality looking images using our ODE. And also another interesting thing is that we can combine it with like some diffusion guidance methods. So some diffusion, in particular, this is classifier-free guidance. In particular, this allows us to sample like using classifier-free guidance as well using our ODE, basically. And the key benefit of something like this is that we can sample with far fewer steps. So in particular, we can get these samples with like around 100 like sampling steps, as opposed to the normal like thousands of sampling steps. And there are other benefits as we like continue pushing this as well. And another like point is that we can derive an elbow for our diffusion model as well. Basically, more or less what ends up happening is that you have this idea of a reflected Gersonov theorem. So you can extend like the standard Gersonov theorem, which is what you use to derive like these maximum likelihood bounds for your standard diffusion models. You can extend this to like the reflected case. And then you basically get like this expected value. This thing is like effectively your elbow, basically, right there. And the key idea behind this is that like the reflected SDEs, they're a limit of your standard SDE. So for your standard SDE, as long as you scale things, if you take a standard SDE and you add to it a vector field, which basically pushes like mass into the domain, and you scale that like outside vector field to infinity, you basically recover like most of the theorems that you would get for your standard SDEs. And we can just do this for our reflected SDEs here. And then once we apply this and we use this maximum likelihood training like setup, we can basically like get commensurate results with state of the art for like likelihood estimation tasks. In particular, like we get like 2.68 and 3.74 bits per dimensions for CFAR 10 and ImageNet32 respectively. The only results that end up beating ours are like our VDM, especially when for VDM, this variational diffusion models. If you apply like a bunch of like extra tricks to it, basically, you need to apply like learn noise schedule, importance sampling, a lot of extra tricks. Once you apply them to VDM, it gets slightly lower scores than ours. But for our stuff, we can basically like get like pretty close scores without like having to apply all this extra stuff as kind of the main intuition. So basically for our stuff, everything's trained together in one good format. We basically, and you can get commensurate results without having to like really like stress like these other important aspects like importance sampling or learned noise schedule. Yeah, and the last thing that I want to talk a bit about is the fact that like for our setup here, for like the entire like reflected diffusion model setup, everything was given kind of like agnostic to the underlying geometry mostly. So basically the key intuition here is that we can generalize our framework to other different types of like bounded domains, let's say like some shapes like given here, like you have these nice shapes, you can learn this nice checkerboard pattern. Also, you can do this for like other like convex sets, stuff like this that people might work with, and basically everything works some out mostly. And then we can in fact also scale up our like geometry as well. So the key idea here is if your omega is like a bounded domain, and if it's diffeomorphic, like except for the boundary to like your standard unit hypercube, well, we can do this kind of latent diffusion idea where we take our omega, we map it to our latent like 0,1 hypercube, and this should be diffeomorphic, it should be like completely like bijective, more or less. And then we can learn diffusion on our hypercube given here, and then we project it back to our initial domain omega. Then this allows us to effectively use the fact that this like score matching, our denoisy score matching objective is particularly amenable for this unit hypercube. This allows us to generalize our framework to like more general geometries and high dimensions. So in particular, we do this for the simplex in one of our examples. So you can imagine this like this three-dimensional simplex or a two-dimensional simplex, but except like with 999 dimensions instead of 2 dimensions. This is what we're able to do. And yeah, that's all I had. I guess any questions?
Yeah, so thanks first of all for the nice presentation, but then let's maybe do a quick takeaway summary. If you go a few slides back where you explain your method, why do we, so we want our reflected distribution. And then why can't we just simply add up the scores reflected, or why can't we just simply add up the probability mass reflected on the domain? And why do we need to, where do the large sums come from? And then how do you fix the large sums? Like, I think that's the main technical contribution here, right? And or the main idea here, and maybe we can just summarize that again.
I think like the main idea, I think like this is one of the technical, I think this is one of the technical points, but I think the main idea will be a bit different. So I can talk about this technical point and the main idea separately, I guess.
Yeah.
But yeah.
Okay.
For this technical idea, yeah, I mean the issue is that once your sigma becomes very large, then summing up our score matching given here is like this infinite sum. This is an infinite sum. All the reflected values of xt is an infinite number.
Why is it infinite? Why do we have multiple reflected values?
Oh, because you kind of like this is what I visualize here is like a one-step reflection. But you can imagine like if you just do it on the other side, so you can like there's another side to it as well. So basically like you do a double reflection. You also have the sum up over all paths, which have a double reflection.
So
what makes
the thing is basically you have if you're at let's say at time 0.1 at time 0.5, then you get the reflections from time 0.4 that the stuff that was reflected there, and then maybe the density that flowed to your current point where you're evaluating the density at time 0.5. And you also get the reflections from 0.3, 0.2, and 0.1. And
yeah, I think for concrete numbers, we can think about it like as follows. If your domain is, let's say, 0 to 1, and your source is, let's say, is like 0.3, then we have to add it up like okay, so we have to add up 0.3, and this is our source distribution. We have negative 0.3. We also have 1.7, and then also on the other side we have negative 1.7 and okay, negative 1.7, and on the other side we have on the other side. On the other side, we have 2.3, like 2.3. So like we basically have like negative 0.3, like 1.7, 2.3. Like, and you can continue like building this up. So like instead of 2.3, it could be like 3.7, 4.3, and then so on, like 3.7, 4.3, then like 5.7, 6.3, and then you keep on adding those up on like the positive side, and you have something similar for the negative side. And this is like and these correspond to like we take like 5 reflections. And you can think of it as like a five reflection path. You hit the boundary and you go back basically. And this is what happens when you expand it out, kind of geometrically speaking. Yeah, so that's kind of like the issue there. And this is like why this sum is infinite.
And now
I think the main idea.
Why can't why do you say good for small values of t? Is there still something that you can do for small?
So if you're for small values of t here, and sorry this was not clear originally. Let's say you have your source distribution. It's at like negative 0.3, 0.3, 1.7, 2.3, etc. Well, if your sigma value is like very small, if your sigma value is like 0.05, then this normal distribution, like the sum that you get from like 1.7 or like 2.3, and let's say your data point is like 0.5. Well, if it's very small, then these things will not matter at all, because it'll be a normal distribution from like 1.7 to 0.5, so a distance of 1.2, but your standard deviation is like 0.05. And then once that happens,
practice, you choose a cutoff where you train with the simple reflection approximation, so to say, and then you use above that cutoff of time, you train with your
harmonic one. This is exactly what happened. So we're able to we're able to get this. This is exactly what happens. This is exactly what happens.
What's the cutoff that you use?
I forget exactly before our 0, 1 case. It was something along the lines of like 0.6 or something like that. And then with between 0.6, we're able to approximate it between with like 3 of like these reflections and like 5 or so like harmonic components. And like, yeah, this ends up mattering because in particular, like we're working with images and we want to keep it like relatively constrained. Otherwise, images will be it'll just be too many. Like you have to multiply your input batch by like a size of 100 and perform a computation there for each pre-processing step, which can get expensive.
Oh, but this is very cool, I think. Okay, and then
I
do you
think, yeah,
think
I think the main
something?
idea,
Mhm.
I think the main idea, I think is going back to this slide here, I think will be the main idea, basically. Like the fact that, we had this thing that's used in practice called thresholding. And this is like what people like normally use in order to get good image results, especially in like the image like pixel space. And it's not principled. And I don't think anybody would argue that it's particularly principled, but it works well in practice. And so our method introduces a way to our method introduces a way to make this thresholding like a hack a bit more principled, and we can draw way more connections with a lot more established theory because of it. I guess would be the main takeaway. Yeah, I think that's what chats.
So what if we have some like some roboter arms like this or something like that and a joint here, and we have a
Yeah,
distribution over the angles here. But the limit is this, like at maximum you can get this sort of extension of the angle and this and this sort of extension of the angle. Would for something like this the reflected diffusion models be useful?
yes. This would be exactly the case where we would want to apply this reflected diffusion model because of the fact that it is bounded, and we have this nice boundary, and we can kind of set it up to be like set up to work. I think Ari asked a question like, can we generalize this premise to general manifolds? And the answer is yes. The broader setup to like, or the broader generalization for our method would be what's like, we generalize the manifolds with boundary effectively. That would be the kind of the categorical lift. And doing this is not particularly, sorry, doing this would not be particularly like I guess conceptually challenging. You basically you have the same idea of like, yeah, this F would be replaced by a vector field. This Brownian motion will be replaced with Brownian motion on a manifold. Like this LT here, this like DLT here, this would also be replaced by something suitable. This would be just like a reflection at the boundary, and you just generalize this pretty easily. I guess the main like difficulty or like the main annoyance perhaps would be the fact that you have to derive the score matching loss for this other formulation, and this could be like challenging depending on what your manifold boundary is. As long as your manifold with boundary is particularly like well behaved, let's say a pretty typical space, I think you should be able to derive like something similar to like what I've done here with this whole like reflection scheme. Like for like small values of t, you do this reflection, and for large values of t, you do this Fourier decomposition. This would work here, and this would generally like everything would generally apply over there as well. Yeah, and that answers the question. And yeah, for the robot arm in particular, this would be an example where you can do this for like, let's say a bounded subset of SO3. I think this would be generally should be possible, but like also it could just be a pain to like implement, kind of.
Very nice, very nice. Yeah, no, I find this extremely cool, this work. And but can you maybe give a comparison quickly? I mean, we already talked about this, but say a few words on how does this compare to these constraint diffusion models, this new paper on constraint diffusion models?
Yeah, I think I haven't read that paper like very deeply, but like I think the main difference is kind of like where the papers like kind of where papers go in direction. So I think for our paper, we focus specifically on reflected diffusion models, because reflected diffusion models, like you have this natural analog of like thresholding. You have like this like stuff that people already use in practice. And because of that, you can, if you build a framework around that, then then we can apply this to images. Specifically, we focus on scalability. That was one of the main things we like looked at. And as such, we're able to like scale up to images. We're able to explain like the thresholding. We're able to derive like very similar principles with respect to like thresholding and like how we do ODE sampling, for instance. And we can like look at that in particular. From what I remember from the other paper, I don't want to like put words in anybody's mouth. I think the main interest, or the main thing that they were looking at in that paper, they were looking at more general bounded domains. Let's say your like convex subsets. And they work from there, and they basically try to say like, what happens if we wanted to define a diffusion model on this convex subset? Well, we can like they have like reflected diffusion as well in some form, but they also like look a lot into like constrained diffusion processes as well, which were like different. But as such, I think they don't focus in particular like on scaling the image size and the ramifications of that, basically. So yeah, basically I would say. Yeah.
Then in the chat, we have the comment. It would be fascinating to generalize it to piecewise manifolds that have abrupt corners.
Oh, what do you mean abrupt corners? I guess because I think you just generalize this to manifolds with corners like as well, because like corners are measure zero. But like, what do you mean by piecewise manifolds? I guess. All right. But for piecewise in particular, what does that mean? Like, are you thinking of like I think algebraic? Are you thinking like algebraic sets or anything like that? Okay. Hello. All right. I mean, well, yeah, I guess yeah. For manifolds with corners, like this generalizes also. Like there are some like caveats kind of with like the time reversal of the reverse diffusion once you add in corners and stuff like that. But really in practice, I don't think this stuff really matters. It's kind of like as long as you're like, let's say in particular, we use the heat equation. So we just like, we remove this f would be 0, our g would be like some scalar. Well, then this should work generally for like most domains, because it's a rather fundamental construct you have. And then with that, you can define like this whole setup basically.
Okay, very cool.
Yeah. Any more questions?
No, I don't think so. Also not from my side. I had a question in mind just now, but it escaped me after this long discussion about manifolds. Yeah, right. What are the scalability issues that come up here? Like, of course, there's this Fourier trick that you're now using, and the harmonic approximation. But what are the scalability differences, I guess? And how is your model impacted differently by a higher data dimension than a usual diffusion model?
Yeah, I think like it all comes down to this thing here, this gradient x log, this gradient x transition kernel. Yeah, like this is like the only thing that like really changes. And in practice, this is what like happens basically. So for our method in particular, because we have this like whole like we sum over the past and we do this like harmonic decomposition, this basic scalability is no longer an issue for our particular case. So when we do this on like your standard unit hypercube, like basically everything's like completely scalable. It scales about as well as standard diffusion models. It's going to be off by like a couple like microseconds really. Maybe it might be some like, I mean, everything basically gets amortized out basically because you do this computation like beforehand. Basically, we're able to do this like computation like about as quickly, if not just as quickly as your standard diffusion model. And we're also like equally as scalable if we're talking about the image domain. Yeah, so previously for your standard diffusion model, this would be like a much more simple closed form. But now, with our tips and tricks, we're able to match it more or less. The issue really comes to like more general domains. So if you have a more general like convex set, how do you like do like this summation term here? So yeah, in particular, if you want to do the sum over paths method for your like more general domain, like, well, how do you do the reflection? It gets kind of like messy like after a certain point, and like things end up becoming a bit more difficult to work with. Basically, this reflection doesn't become as nice. And another issue is that like these harmonic components become like you can't get them in closed form basically if you're working with something a bit more general, I think. And so because of that, this like impacts the scalability because like again, you can't really apply our stuff that out of the box to it. I think it's still possible to do it, but like it's just generally a bit more of a pain, and it generally scales slightly worse with dimension. So I think yeah, this was the point of our like last slide here. If I can go, yeah, which is basically the fact that we noticed that like for our more general domains, omega, most of the time they're going to be like diffeomorphic. Like they're going to have the same topology as your standard unit hypercube because it's going to be like some convex set. They're all based. It's they could be. It's all basically the same except maybe a couple of smoothest issues. And because of that, by doing this like latent diffusion type of thing where you map to a different space and then you map back, except in this case, it will be completely like diffeomorphic. Well, then we can basically scale like by applying this to our more scalable unit hypercube case, I guess. So generally, like, yeah, I think for scalability, it's like a bit more, it can get a bit more tricky, but like with some proper insight and some proper like work, you can make it like equally as scalable. Standard diffusion models, equally as quick and scalable, I guess.
Okay, I guess that also answers the chat question about how scalability or how you impact training.
I think this is mostly for I think this is mostly for training. I guess inference you have to compute like the reflections at each time step, but this is very minor. This is a very minor computational cost. So yeah, basically it's like it's the main idea is for training. Inference, inference doesn't really play much of a factor because of the fact that like computing the reflection or when computing this projection operator is normally pretty cheap compared to a neural network. Yeah.
Great, fantastic. Then I would say we call it a day here, and thank you for presenting this very nice work to us. Thanks for explaining your work.
Thank you for your kind words on it. Yeah.
Likewise. Then we'll see you guys next week, and everyone have an awesome week. Bye, except for Aaron. If you stick around for a minute, that would be great.
Sure.
And to everyone else, I hope you have a nice week and enjoyed this session as much as I did. Bye. See you, everyone. Yeah, because Aaron, you maybe seen the Twitter advertisements that we always make here, and if we have a YouTube video, right? So we would put the recording of the session on YouTube, and then we would put a little clip on Twitter of just audio where you give like a 10-15 second introduction of what this is about, and then we have this little audio clip as advertisement. If you want to do something like that, then we would record this audio clip right now. So
all right, let me think of something to say. I guess.
Great. In the meantime, I put some people in the waiting room.
Okay, let me think here.
There will be no video, right? Only audio.
Yeah, only video. Let me just go to my blog post actually. Yeah, I can just give it here. I can just give the thing here. Does this work?
So I will usually do something more like we all know and love the diffusion models for generating our nice cat images, but people actually do the stupid thing of
It's right here. That's what they say. That's what they say here.
Okay. Fair.
All right. Okay, I mean, I can rephrase this slightly, but yeah, I'll also say from the top, 3, 2, 1. Okay, let me take a drink of water before I do it. Yeah. So, and diffusion models are trained to reverse the stochastic process through score matching. But a lot of diffusion models rely on a small but critical implementation detail called thresholding. The main idea behind thresholding is that you want to project the sampling process to the data support after each discretized diffusion step, and this stabilizes generation, but breaks the theoretical framework. Interestingly, as one limits the number of steps to infinity, thresholding converges to a reflected stochastic differential equation. In our work, we discussed this connection to develop reflected diffusion models, which correctly train for thresholded sampling, respect general boundary constraints, and generalize many of the pre-existing features of standard diffusion models.
Very interesting work, in my opinion. And if you want to extend this to some more elaborate applications than just images, I think there might be very cool stuff that can be done here. And if you want to join future reading group sessions yourself, then all the information is down in the description. See you on some Monday.